Using a duplex metal-clad cable connector for a single metal-clad cable is not permitted according to electrical codes and best practices. A duplex connector is specifically designed and listed for securing two metal-clad cables simultaneously. Using it for only one cable violates its listing and intended purpose. Firstly, the connector's clamping mechanism is designed to evenly distribute pressure across the jackets of two cables, ensuring a secure and reliable connection. When only one cable is installed, the clamping force is unevenly distributed. This uneven pressure can damage the cable jacket, potentially compromising the insulation of the conductors inside. Such damage can lead to short circuits, ground faults, or even electrical fires. Secondly, electrical codes such as the National Electrical Code, or NEC, require that all electrical components be used in accordance with their listing and labeling. This means that a duplex connector must be used with two metal-clad cables as specified by the manufacturer and any relevant standards. Using it for a single cable is a direct violation of this requirement. It creates a non-compliant and potentially hazardous installation. Thirdly, improper use of connectors can create issues during electrical inspections. Electrical inspectors are trained to identify installations that do not meet code requirement. A duplex connector with only one cable present will be flagged as a deficiency, requiring correction. This can result in project delays, added expenses, and potential legal liabilities. When installing metal-clad cable, it is crucial to select the correct type and size of connector for the specific application. For a single metal-clad cable, a single barrel connector designed for that purpose should always be used. These connectors provide a secure and code-compliant connection without the risks associated with misusing duplex connectors. Several types of single metal-clad cable connectors are available, including set screw connectors, compression connectors, and snap-in connectors. The choice of connector depends on factors such as the size of the cable, the type of enclosure or junction box being used, and the specific requirements of the installation. Set screw connectors are a common and versatile option. They feature one or more set screws that tighten down onto the cable jacket, providing a mechanical grip and electrical bond. Compression connectors offer a more robust and reliable connection. They use a compression ring that is crimped onto the cable jacket, creating a gas-tight seal and superior mechanical strength. Snap-in connectors are designed for quick and easy installation. They typically feature a spring-loaded mechanism that allows the cable to be inserted and locked into place without the need for tools. Regardless of the type of connector chosen, it is essential to follow the manufacturer's instructions carefully during installation. This includes ensuring that the cable is properly stripped, inserted into the connector, and secured with the correct torque or crimping force. It is also important to inspect the connection after installation to verify that it is secure and that the cable jacket is not damaged. In addition to selecting and installing the correct connectors, it is also important to adhere to other relevant requirements of the National Electrical Code. This includes ensuring that the cable is properly supported, protected from physical damage, and grounded in accordance with the code. Section 330 of the NEC covers metal-clad cable, outlining specific requirements for its installation and use. Some key considerations from this section include: firstly, metal-clad cable must be supported and secured at intervals not exceeding 6 feet. Shorter intervals may be required in certain applications, such as where the cable is subject to physical damage or vibration. Secondly, metal-clad cable must be protected from physical damage where it is exposed to impact or abrasion. This may involve installing the cable and conduit or using other protective measures. Thirdly, metal-clad cable must be grounded in accordance with the requirements of Article 250 of the NEC. This typically involves connecting the cable's metal sheath to a grounding electrode conductor or equipment grounding conductor. Fourthly, metal-clad cable must not be used in certain hazardous locations, such as those containing flammable gases or vapors, unless it is specifically listed and marked for such use. It's important to note that electrical codes and regulations can vary depending on the specific jurisdiction. Always consult the local electrical code and any applicable amendments to ensure that your installation complies with all requirements. When in doubt, it is best to consult with a qualified electrician or electrical inspector. They can provide guidance on the correct selection and installation of electrical components, ensuring a safe and code-compliant installation. Making unauthorized modifications to electrical equipment or using components in a manner not intended by the manufacturer can create significant safety hazards and legal liabilities. Electrical work should always be performed by qualified individuals who have the necessary knowledge, skills, and experience to do the job safely and correctly. Furthermore, electrical installations are subject to inspection by local authorities. Inspectors verify that the work complies with applicable codes and standards, ensuring the safety of the building's occupants and the integrity of the electrical system. Failure to comply with electrical codes can result in fines, project delays, and even legal action. Therefore, it is crucial to prioritize code compliance in all electrical work. In summary, using a duplex metal-clad cable connector for a single metal-clad cable is not permitted. It violates the connector's listing, compromises the integrity of the cable, and creates a non-compliant installation. Always use the correct type and size of connector for the specific application and adhere to all applicable electrical codes and regulations. Doing so will ensure a safe, reliable, and code-compliant electrical system. Proper grounding and bonding are critical aspects of electrical safety. Grounding provides a low-impedance path for fault current to return to the source, allowing overcurrent protection devices like circuit breakers or fuses to quickly interrupt the circuit in the event of a ground fault. Bonding ensures that all metal parts of an electrical system are electrically connected, minimizing the risk of electric shock. Article 250 of the National Electrical Code provides detailed requirements for grounding and bonding. Key aspects of grounding and bonding include, firstly, the grounding electrode system. This system consists of one or more grounding electrodes, such as ground rods, ground plates, or underground metallic water pipes, that are connected to the earth. The grounding electrode system provides a reference point for the electrical system and helps to stabilize voltage. Secondly, the equipment grounding conductor. This conductor provides a low impedance path for fault current to return to the source from metal parts of electrical equipment, such as enclosures, raceways, and appliances. The equipment grounding conductor is typically a green insulated wire or a bare copper wire. Thirdly, the bonding jumper. This conductor connects metal parts of an electrical system to ensure electrical continuity and minimize voltage differences. Bonding jumpers are used to bond together metal conduit, metal enclosures, and other metal components. Fourthly, ground fault circuit interrupters, also known as GFCIs. These devices are designed to protect people from electric shock by detecting small imbalances in current flow and quickly interrupting the circuit. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas. Overcurrent protection devices, such as circuit breakers and fuses, are essential for protecting electrical circuits from overloads and short circuits. These devices are designed to automatically interrupt the circuit when the current exceeds a predetermined level. The National Electrical Code provides requirements for the selection and installation of overcurrent protection devices. Key considerations include, firstly, the ampacity of the conductors. The overcurrent protection device must be sized to protect the conductors from overheating. The ampacity of a conductor is its current carrying capacity, which is determined by its size, insulation type, and ambient temperature. Secondly, the interrupting rating of the device. The interrupting rating of an overcurrent protection device is its ability to safely interrupt a fault current. The interrupting rating must be high enough to handle the maximum fault current that could occur at the point of installation. Thirdly, the type of device. Different types of overcurrent protection devices are available, such as circuit breakers, fuses, and supplementary protectors. The type of device selected should be appropriate for the specific application. Electrical safety is paramount in all electrical work. It is essential to follow safe work practices and use appropriate personal protective equipment to minimize the risk of electric shock, arc flash, and other electrical hazards. Key safety practices include, firstly, always energize circuits before working on them. Use a voltage tester to verify that the circuit is energized before touching any conductors or components. Secondly, use insulated tools and equipment. Insulated tools and equipment can help to protect you from electric shock if you accidentally come into contact with a live circuit. Thirdly, wear appropriate personal protective equipment. This may include safety glasses, gloves, and arc-rated clothing. Fourthly, be aware of your surroundings. Watch out for overhead power lines, wet locations, and other potential hazards. Regular inspection and maintenance of electrical systems are essential for ensuring their continued safety and reliability. Inspections can help to identify potential problems such as loose connections, damaged insulation, and overloaded circuits. Maintenance can include tightening connections, replacing worn components, and cleaning equipment. The National Electrical Code provides guidelines for the inspection and maintenance of electrical systems. Regular inspection and maintenance can help to prevent electrical failures, reduce the risk of electrical hazards, and extend the life of electrical equipment. Additionally, it's important to ensure proper coordination between different electrical components to maintain a safe and efficient electrical system. For example, selective coordination of overcurrent protection devices ensures that only the closest upstream device trips during a fault, minimizing disruption to the rest of the system. Voltage drop is another factor to consider in electrical installation. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The National Electrical Code provides guidelines for minimizing voltage drop by selecting appropriately sized conductors. In conclusion, electrical work requires a thorough understanding of electrical codes, safety practices, and the proper selection and installation of electrical components. By prioritizing safety, code compliance, and best practices, you can ensure a safe, reliable, and efficient electrical system. The information provided here is for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified electrician or electrical inspector for specific guidance on your electrical projects.